Hi everyone, my name's Mollie and I'm at the University of Manchester as part of the Spinnaker team. I'm going to be presenting some of my PhD work today, which is talking about modelling neural dynamics on neuromorphic hardware. So there are several custom neuromorphic platforms which are designed to model brains, and they exist for the simulation of spiky neural networks, or SNNs. These generally enforce a simple leaky integrate and fire, or LIF neuron model. The LIF model is really efficient, which is what makes it good for neuromorphic hardware, but it does simplify a lot of biological features, which leads to the loss of some biological characteristics, including ion channel currents. These currents have the ability to change the response of neurons, adjust their firing frequencies, and compute operations such as the exclusive or XOR operation. More biologically accurate models do exist, which are more complex. They can describe these ion channel currents in more complex neural morphologies, but these models add mathematical complexity, and they therefore generally require HPC platforms for their simulations. Neuromorphic systems provide low-power solutions, but the processors from these systems often achieve this by sacrificing precision, and this limits the complexity of neural modeling available. Spinnaker is software programmable, so that means it's quite flexible and it allows the testing of new neural models. So in this work, we present a two-compartment neural model, which is implemented on Spinnaker, and it demonstrates superiority to the simple LIF neuron in that it can perform some biological operations which the LIF cannot. And here we demonstrate it performing the XOR operation. So the model that we've created is a two-compartment model, so it's got dendrite and a soma. This is based on a really large-scale multi-compartment neural model, which was published in Science last year. This model that they presented was really impressive, and it demonstrated some really interesting dynamics. So the aim of our work was to kind of simplify that model to make it suitable for neuromorphic hardware while maintaining the interesting capabilities that they demonstrated. So both compartments in the model are able to generate their own spikes, and the membrane voltage in each compartment is calculated with the cable equation. The IM term in the cable equation is the current per unit area, and that's the term where the ion channel conductances are modeled. The somatic compartment in this model has sodium and potassium currents, and the dendrite has a calcium current. This calcium current gives rise to action potentials called dendritic calcium action potentials, or DCAAPs, and it's these DCAAPs which give the neuron model the ability to compute the XOR operation. So the way that the XOR ability is demonstrated here is through three pathways. So we have two excitatory pathways and one inhibitory pathway, which we use to simulate the dendritic compartment. So if you just simulate this neuron with pathway 1 or just pathway 2, then the blue line here is the membrane voltage in the dendrite. So you see that you get these nice dendritic calcium action potentials. If you combine pathway 1 and pathway 2 together, you then lose the action potentials. And if you add in your inhibitory pathway as well, so you simulate all three pathways together, then they come back. And this kind of biological operation would previously have required a network of leak integrate and fire neurons, but we've now shown that you can do this kind of operation with a single neuron model if you incorporate this calcium current. So the next thing that we had to do with this was then implement it on Spinnaker. Our aims for this model on neuromorphic hardware was to achieve a model that's both fast and correct. So the speed is achieved through parallelization on digital neuromorphic hardware, and the accuracy was validated against a double precision floating point reference simulation. So that was in Python. The main problems that we faced with this implementation were due to the complexity of the mathematical equations involved in the calculation of the calcium current. These complex equations calculated with the 32-bit fixed point arithmetic on Spinnaker made achieving the speed and the accuracy a bit of an issue. But the way that we overcame this was by using a lookup table. So we pre-calculated a lookup table and loaded it on Spinnaker for the calculation of the calcium current, which significantly increased the accuracy of the simulations and accelerated the solving of them. So this is just a single DCAAP simulated on Spinnaker and compared to Python. So to sum up, This model provides the first implementation of a single neuron model with XOR solving capabilities on neuromorphic hardware. And it was achieved through incorporation of more biologically accurate features to the simple leak, integrate, and fire model. The efficiency of the model could be further increased with hardware accelerators, which would allow the possibility of real-time SNN simulations with more biological realism. Thank you.